welcome to another math talk. Today we have with us Anasmit Pal of B.Math third year. He is primarily interested in geometry and topology. Today he is going to speak about discriminants of polynomials through the lens of Galois theorem. Over to you, Anasmit.
Thank you, Alkopi. So good morning everyone. So today I'll be speaking on discriminants of polynomials through the lens of Galois theory, and I'll keep this talk fairly simple enough for all of you to understand. So without any further delay, let's start. Okay, so Galois theory, a brief. Galois theory bridges the gap between field theory and group theory, and it was originally introduced by Evariste Galois. Galois theory primarily deals with roots of polynomials and their permutations, and we primarily compute Galois groups of polynomials over a base. Also, Galois theory has some geometrical significances. One astounding significance is that we can explain why an angle cannot be trisected using ruler and using compass and straight edge constructions. Also, it specifies when a polynomial can be solved by radicals. So, what do we mean by solved by radicals? For example, if you consider any general 3-degree polynomial, for example, say a3x square, x square, x plus n. This has a general formula. This is given by Cardano's formula, and this is also true for degree 4 polynomials, and for degree 2 polynomials it's simply the quadratic formula. But when one goes to degree 5, one can see that for degree 5 polynomials there exists no such general formula. So we call this insolvable or can't be solved by radicals. That is, there exists no explicit formula for it. Okay. So now we'll see what a Galois extension is. So let K by F be a field extension, and automorphism of K over F denotes the automorphism of K which fixes F. That is, if X lies in F, then if X lies in F, then if sigma lies in automorphism of K over F, then sigma X is X, that is, it always fixes X. Okay. So, couple of terms. First of all, what do I mean by algebraic? By algebraic, I mean that if K over F is a field extension and alpha belongs to K, then there exists a polynomial Px over F such that P alpha is a root of Px. So this is algebraic, and so let alpha belongs to K be algebraic over F. Then for any sigma belongs to K over F, automorphism of K over F, sigma alpha is also a root of the minimal polynomial. Minimal polynomial, what is that? So minimal polynomial over F of alpha is nothing but a polynomial which is irreducible and monic. Moreover, if fx is a polynomial such that f of alpha is 0, then this minimal polynomial has to divide fx. So kind of it's on minimality in the sense it divides all those polynomials whose roots are alpha. Okay. So this is fairly simple proof. Let me show you. Suppose alpha is algebraic, then it satisfies its minimal polynomial. So this is the minimal polynomial. Now, where ai's belong to F. So if we apply the automorphism sigma on both the sides, we will get sigma alpha bar n plus sigma of n minus 1 alpha bar n and so on. And now, from the property of automorphism, this n comes out as it is already fixed by sigma, and so we get this one. So this is nothing but we have replaced sigma alpha in place of alpha. So we can tell that sigma alpha is also a root of the minimal polynomial. The sigma alpha is a root of the minimal polynomial. Okay, so in other words, the roots of the minimal polynomials gets permuted by the action of sigma. So it does not matter if we apply sigma over alpha, then sigma alpha is a root of the minimal polynomial. Okay, so we call this action to be a transitive action on roots. So what do I mean by transitive action? By transitive action I mean So suppose X is a set and G G acts on X transitively, it means that for all x comma y belongs to X, there exists a sigma belongs to G such that sigma of X is 1. So this is called the transitive action. In simpler words, we can reach to any element from any element using sigma. Okay. So for example, consider the field extension k equals q root 2. So again, what is a field extension? We basically attach a root. For example, if we want to define, suppose f is a field, and then we wonder what is f of alpha, where alpha belongs to some extension k. So basically, this is nothing but we take the polynomial ring over fx and we mod it out by the minimal polynomial of f over alpha. Now, notice that I told this minimal polynomial is monic and irreducible. So, this is a field, and hence this is also a field. By this I mean we attach a root of the minimal polynomial to f to get the field extension. Right? So for in this example, we consider the field extension k equals q root 2 over f equals q. And so if tau belongs to automorphism of k over f, the minimal polynomial of root 2 is x squared minus 2. It's simple to calculate. So remember that I said in a minimal polynomial the roots get permuted. So if tau belongs to automorphism of k over f, so it has only two possibilities. Either it maps root 2 to itself, or it maps root 2 to minus 2. So we have two possibilities. So we can completely determine tau. So any element in q root 2 is of the form a plus b root 2, and as a and b will be fixed by tau as it belongs to f, we will get a plus minus b root 2. Where this a plus b root 2 to a minus b root 2, we call this the conjugation. Basically it changes the sign. We denote it by sigma. So this is nothing but the automorphism of k over f is nothing but 1 sigma, and clearly this is isomorphic to z by 2z. So this is an example of Galois extension. Okay. Now let H be a subgroup of automorphism of K. And what is K? K is a field extension of F. Then the collection of F, the collection F of elements of K fixed by the elements of H is called the fixed field of H. Okay, so here I will state a proposition, fair enough simple. So this is groups of fields are associated via reverse inclusion. For example, if F2 is the extension of F1 with two subfields of K, then we get the reverse inclusion. Automorphism of K over F2 is a subgroup of automorphism K over F1. So I will be giving an outline of this group. It's fairly simple enough. If sigma belongs to automorphism of K over F1, this implies that, sorry, K over F2, it implies that sigma fixes F2, right? But we have F2, F1 is contained in F2. So sigma also fixes F1, which implies sigma belongs to automorphism of K over F1. So we get this inclusion. And similarly, if H1, H2 be two subgroups of automorphism of K, then this is the symbol for the fixed field of H. Then fixed field of H2 will be a subfield of fixed field of H1. And the proof goes similarly. I'm not proving that. Okay. Okay, so this is a theorem. This theorem you can refer to modality or Vandermonde or any other standard Galois theory text. Then the theorem states that if E be the splitting field of a polynomial fx over capital F, then automorphism of E over F, modulus of automorphism of E over F is less than the degree of E over F. And this equality holds if fx is separable over F. So what do we mean by separable? it's fairly simple in our definition. Fx is separable if all roots are disjoint. Simple in our definition. Also another definition, it will not be required. Suppose gx is a polynomial, then this is purely inseparable if it has only one root. If it has only one root, that is, suppose x minus alpha power n. This is purely inseparable extension because it has only one root. Right. So in this term, mainly we will be concerned about separable polynomials. Right. So this equality holds if and only if fx is separable over f. So this is the main definition of our term. Let k by f be a field extension. Then k is said to be Galois over f, or k over f is said to be a Galois extension if automorphism of k over f is equals degree of extension of k over f. So basically this inequality, this becomes equality. And the group defined by automorphism of k over f, we will denote it as Galois group of k over f. Clearly, if k is the splitting field of a separable polynomial over f, then f is the extension is Galois. Oh. Galois group of polynomial is a Galois group of its splitting field over the base field. So basically, you take one polynomial, you find a splitting field. Then suppose the splitting field is k. Then automorphism of k over f is nothing but Galois of k over f. That's the definition. Okay. Okay, let us consider an example. Consider this biquadratic extension. So what is this? Basically, this is q of root 2 and root 3 attached over q, and we will show that this is Galois. So first of all, let me explain what I mean by q root 2 comma root 3 over q. So basically, at first you take q, then you attach q root 2, you attach root 2, and then you again attach root 3 to this one. So this is nothing but q root 2 root 3. Also, this is a biquadratic extension of degree 4. Moreover, it is the splitting field of x square minus 2 and x square minus 3. So basically, we took one root of this, another root of this, and just attached it to q root 2 root 3. Right. So, if I have to determine the automorphisms, the possible automorphisms are, see, I told that in an, okay, so these are irreducible over q, right? So, the root of this, if we apply sigma over root of a irreducible polynomial, then it must map to root of that irreducible factor. So, the possible isomorphisms would be root 2 goes to plus minus root 2 and root 3 goes to plus minus root 2. Right. Also, you can solve it. It's a fairly enough easy exercise. Why can't this be possible? This one. Why? Okay, so these are the possible isomorphisms. So we get 4 possible isomorphisms. And if we denote the second and the third one by sigma and tau, then you will notice that the fourth one is nothing but the composition of sigma and tau. Hence, this Galois group is nothing but 1 sigma. 1 is the identity map, 1 sigma, tau and sigma tau. And this is isomorphic to B4. And this is called the Klein 4. Okay. Now we come to fundamental theorem of Galois theory. So this is the most important theorem in and probably the art of Galois theory. So notice the similarity of both the diagrams. Here f and g are sigma and tau respectively, which I defined in the previous slide. So notice that. Okay, so let me go to the previous slide. sigma is nothing but root 2 goes to minus root 2 and root 3 goes to root 3. This is sigma. Okay, now observing this diagram, the fixed field of this group is q over root, because see, this fixes root, right? Similarly, if you take fg, that is sigma tau was root 2 goes to minus root 2 and root 3 goes to minus root 3. So if you multiply these two, you get root 6. So one thing for sure, that root 6 is fixed. So the group 1 fg, the fixed field of that group is q root 6, and similarly the fixed field of 1 comma g is q root 2. And of course the fixed field of 1 would be q of a root 2 or root 3, and of this will be q. So you notice that this is kind of a reverse inclusion, which I proved earlier. Oh. So let me state the fundamental theorem Galois theory. So I will state it without a proof, and we'll use it very often in this talk. Okay. So let K by F be a Galois extension and let G be the Galois group. Then there exists a one-to-one correspondence between the subfields of K containing F, that is between E, and the subgroups H of G, that is this. And the correspondence is given by you take the subfield and you map to the elements of G fixing E. And again you take a subgroup and map it to the fixed field of H. We can easily show that this is an inverse map kind of thing. So this is a one-to-one correspondence. Okay. And some further properties. Moreover, we have if E1 corresponds to H1 and E2 corresponds to H2, that is these are the fixed fields of that groups respectively. Then this I showed earlier, the reverse inclusion thing. E1 is a subfield of E2 if and only if H2 is a subgroup of H1. Right. Another thing. Okay, let me draw some diagrams, or else it will be hard to explain. So we have the correspondence. So this degree of extension K over F is nothing but the order of this group. And again, the degree of this extension is nothing but the index of H over G. So you can see this clearly. This goes to this and this goes to this. Also, K by E is always Galois, and with its Galois group being H, it can be shown. But for this is Galois if it can be shown that H is a normal subgroup of G. Then we'll have Galois of E over F is nothing but G quotient with H. This is true if and only if H is a normal subgroup. Okay. So now the next idea that we'll go into is norms and traces in Galois theory. So this topic goes hand in hand with linear algebra. Okay. So let K by F be a field extension, be a finite extension with the index being n, and let A belongs to K. We fix an element A belongs to K, and we define a map LA from K to K, where it maps B to A multiplied by B. So one thing you can notice or you can check that this is an A vector space homomorphism. This is nothing but a linear transformation, because we consider the field extension to be a vector space over the base field. And we know that corresponding to every linear transformations, there is one matrix representation. So there will be a matrix over the base field MNF. Right. And this is nothing but the set of linear transformations from K to K. So this is an isomorphism. Okay, so for finite extension K over F, we define a norm and trace for A to B. Norm of A is nothing but the determinant of this matrix or the determinant of this transformation, and trace over of A is nothing but the trace of this linear transformation. Okay. So let us see some computations. Suppose we consider the quadratic extension f root d, and we assume that d is not a square in f. If d was a square, then d would already be in f, and that would be the field itself. So there's nothing interesting in that. Okay, so for a quadratic extension, we have the basis 1 comma root d, then any alpha can be expressed in the form a plus b. Okay, and as this is nothing but the multiplication map, L of alpha is nothing but a times L of 1 plus b times L of root d. Now we need to calculate this L1 and L of root d. So one thing is for sure, we can understand that this L1 is nothing but the identity map, and we want to calculate L root d. So for calculating L root d, we'll examine the action of L root d over the basis elements 1 and root d. So over 1, this will be 0 times 1 plus 1 times root d, and L of root d times root d is nothing but d, and this will be d times 1 plus 0 plus d. And so the matrix will be this 0 goes there and 1 goes there, standard linear algebra tricks, and d goes here and 0 goes here. So L root d is nothing but this matrix. And again, if we add everything, we get L of alpha is a b times b a. Okay, and our norm and trace will be the determinant of this matrix and the trace of this matrix respectively. So if you calculate the norm, it will be a square minus b square d, and the trace is clearly 2. And also you can calculate, in particular we have norm of a over f root d is minus d, and the trace is right. But every time this is not possible for us to calculate this by computing a matrix, because this is a fairly simple extension. This is nothing but the quadratic extension. It might be possible that you attach n many roots or n many elements, and then for the calculation of these matrices over these matrices would be cumbersome. So we devise another plan. Okay, so some standard properties of norms and traces are. So for all A belongs to K, norm of A and trace of K will belong to F. These are easy to prove. These are just basic linear algebra tricks. Again, the trace map is an F linear transformation, and I can show the last 3 proofs. These are not proofs, these are just basic computations. Okay, so if alpha belongs to F, one thing we can understand that L of alpha is nothing but alpha times L of 1. So the matrix will be alpha like this, right? So the determinant will be n of alpha, and the trace will be alpha times. And again, by the properties of determinant, we can comment that norm of A is nothing but norm of A times norm of B, because the determinant is multiplicative, right? So now we will take the help of the minimal polynomial to calculate the norms and traces. Again, I will state this theorem without a proof, because the proof is a bit lengthy. Okay, so theorem, let A by F be an extension of degree n, and Bx this be the minimal polynomial of A over F. Then we have norm of this is this, and norm of trace is this. So one thing you might have noticed that we can use this theorem to prove this, that this always belongs to the base field, because these coefficients are nothing but elements over F, right? Now, for example, we can consider take the base field to be Q and the extension to be Q of cube root of root 3. Then the minimal polynomial is x cube minus 2, and from this you can compute that from these two coefficients that the norm is 2 and trace is clearly 0, because the coefficient of x squared is 0. So this formula is handy. Okay, so we mainly use this formula, not the previous one. Another thing, if K over F is a Galois extension, then and alpha belongs to K, the elements sigma alpha, where sigma ranges over the entire Galois group, are called the Galois conjugates. And another theorem, this can also be proved, but I am not stating the proof. The norm of A is nothing but the product of all the Galois conjugates, and trace is nothing but sum of all the Galois conjugates. So, if you have done the LA2 course, you can find a similarity in the definitions with determinant and trace of a matrix, where we state that the norm or the determinant is the product of the eigenvalues, and trace is nothing but the sum of the eigenvalues. So this kind of runs hand in hand with that, but it's not entirely simple. Okay, so we now come to the main plot of this topic, right? So let K by S be Galois, and K be the splitting field of some separable polynomial over F. Okay, so now for all sigma maps the root of an irreducible polynomial to itself. And as sigma is fixed over F, it is uniquely determined by its action on the roots. So for example, if you take a field like this alpha 1, alpha 2 up to alpha n, then as sigma is fixed over alpha, we only need to determine the action of sigma over this alpha. So this is similar to the notion that in linear algebra we can simply define the linear transformation set P over the basis elements only. We need not define that over the whole field or the whole vector space. So this is similar to that. So if we fix the labeling on the roots, say alpha 1, alpha 2, alpha n, say this is 1, 2, 3, like we fix the labeling, then every sigma belongs to the alpha K over F. This can be understood as a permutation of this, or the permutation of the roots. And so, as we get this permutation, we can understand that this Galois group, Galois of K over F, is nothing but the subgroup of S. Right? Okay, so this was for one irreducible factor. And if we consider K irreducible factors, then say you take the ith factor and say one root is alpha, and if you map sigma of alpha, then suppose say this is beta, then beta is also root of that irreducible polynomial, not the others. And for this we can get the injection to Sn1 cross Sn2 cross Snk, where the degree of each fi is ni. And why did I take the direct product? So to state vaguely that every root of the irreducible polynomial stays within itself. It does not interact with those of the other two irreducible factors. Okay. And we saw that the action of G on the roots of irreducible polynomials is transitive. So if we want to search for the possible Galois groups, then we will only search for transitive groups and nothing else. This helps to reduce the possibilities for the Galois group of the polynomials. Okay. Again, consider the biquadratic extension Q of root 2 root 3 over Q. And recall that we had sigma as this map and tau as this map. And if you put a labeling on the roots, root 2 minus root 2, root 3 and minus root 3, then sigma can be identified with the transposition 1, 2, and tau can be identified with the transposition 1, 3, 4, because this can map to this only and this can map to this only. Okay. And so we get the Galois group of Q root 2 root 3 over Q to be this. And again, this can be shown to be isomorphic to V2. So Galois group of x square minus 2 and x square minus 3 is nothing but V2, the line 2. Okay, so let us see some definitions. So let x1, x2 up to xn be indeterminants. Then elementary symmetric functions are nothing but, you first define S1 to be the sum of all these indeterminants, then S2 be take 2 at a time, then the product of 2 at a time, and then define the sum. Similarly, you take S3 to be the sum of all the products taken 3 at a time, and continue this up to Sn. So this is similar to the coefficients of polynomials, right? they're similar to coefficients of polynomials. Like the first coefficient is the sum of roots, the second one is taken 2 at a time, and similarly the last one is nothing but the product of the roots. Okay. So these are all the elementary symmetric functions. And we define the general polynomial of degree n to be x minus x1, x minus x2 up to x minus xn. That is nothing but the polynomial formed by those elements, those indeterminates, where x1, x2, xn are the indeterminates. These are the roots of that polynomial. Okay. Okay, so by induction, one can easily show that the general polynomial will be of this form, where these are the symmetric functions I defined earlier. And for this field, notice that f of x1, x2, xn, and if we attach these s1, s2, sn to f, this is a Galois as this element, not this field, that f of x1, x2, f of x1, x2, xn is, this is the splitting field. This is the splitting field of the general polynomial. Right? Because we just attach the roots x1, x2, xn, and thus we get the splitting field. Okay, so let Sn act on the rational functions by sigma of p x1, x2 up to xn. These just interchanges this xi's. See, 1 maps to sigma 1 and 2 maps to sigma 2, etc. And so Sn can be, okay, so these are nothing but automorphisms of this, automorphisms of x1. And so Sn, as this acts on the rational functions, this can be identified as a subgroup of that automorphism. So, one thing we can say that f of s1, s2 to sn, these are contained in the fixed field of Sn as these are symmetric polynomials, and if we apply any sigma over elements of this, the polynomial will remain unchanged. So these are contained in the fixed field of Sn. And also notice that, okay, not notice, let me state a theorem. So not a theorem, it's like of a lemma or a claim. So the claim is that if, say, K is a splitting field of polynomial of degree n over f, then the index of k over f is at most n factorial. And let me give a short proof. This is a very easy proof. So first start with, let the polynomial be fx and k be the splitting field of it. So what do? We keep on attaching roots, and so let me show. We keep on attaching some roots. So let fx be the required polynomial. So when we adjoin one root of f to this, let f1 be some f times alpha. So we adjoin one root of this polynomial to this, and the extension that we get, this will be at most n. And when will it be equal to n? It will be equal to n if this is irreducible. Okay. So we get this, say f1 is this alpha. Now, over f1, this f factors as, we took one root. So this is some L times f1, where L is the collection of all the linear terms, because we attached one root of f over this, and a term multiplied by some f1. Right. So now again, this is over capital F1. So again, what we do? We take one root of f1 and then attach it to f1. So let this be alpha 1, and then we define f2 to be f1 of alpha 1. Again, this is a collection of linear terms. So this extension will be of at most n minus 1 degree. Right. So if we continue like this, then by the multiplicativity of the degrees, we get that something like this is true. Clearly, this will be less than n factorial. Okay. So we'll be using this. So as I showed that this f of x1, x2, xn, this will be the splitting field of the general polynomial over this, and so this will be less than n factorial as the general polynomial is of degree n. So we get this to be less than n factorial. So what we can say is, we have this field of x1, x2, x3, or xn. Sn. And here will be the fixed field of Sn, because this is less than n factorial, and this index is precisely n factorial. But also we had shown that f of s1 up to sn is a subfield, the fixed field of sn. So using these two, we can finally conclude that f of s1 up to sn is nothing but the fixed field of sn. We get two inclusions, and then we prove the equality. Right. Okay. So a rational function is symmetric if it is not changed by the perturbation function. And again, I proved it earlier. This one, a fundamental theorem of symmetric functions. Any symmetric rational function is nothing but a rational function in f of s1 s2, because this is nothing but the fixed field of this. So consider some examples. Some examples are, suppose x1 minus x2 whole square, and you can, if we permute x1 and x2, it does not matter because of the square sign. So this is a symmetric function, and if we write it in these terms, then it is nothing but s1 square minus 4s2. So ultimately we can express it in a polynomial in s1 and s2, or the SI, the symmetric functions. Similarly, these are also. Okay. Now, discriminants. So if we consider the quadratic ax square plus bx plus c, its roots are given by the quadratic form. And if alpha 1 and alpha 2 are its roots, observe that if we take the difference and square it, we get nothing but the discriminant, right? So using this idea, we define discriminants in a more general term. So we define the discriminant of the polynomial to be all those products over alpha of alpha I minus alpha j square, where I is, this will be less than j. I is less than j. Otherwise it will be 0. Okay. So notice that D is a symmetric function in x1, x2 up to xn, and hence is a polynomial in D can be expressed as a polynomial in the symmetric function. Okay. Okay. So one thing we need to recall is that we could define the alternating group, which is a subgroup of the symmetric group, by all those elements of Sn fixing this. So why is it true? So if delta the product xi minus xj, then for all sigma belongs to Sn, we can define sigma of delta to be nothing but the sine of sigma times delta. We can prove this. So one way to prove it is consider the transposition decomposition. of a given set. So either we have two choices, this plus or minus 1. And so when I say that this delta will be fixed, I mean that the sign will be plus 1, and that happens even only if sigma belongs to n. That is, it can be expressed as a product of even number of transformations. Right. So, by the fundamental theorem, we can say that the fixed field of f of n is generated by root, because all the elements of n fix this root b, right? And it is a quadratic extension. So one proposition: if characteristic of f is not true, we take this assumption to avoid trivialities. Then sigma belongs to Sn is an element of n if and only if it fixes root b. This was the theorem I stated. And the corollary: the Galois group of fx is a subgroup of n if and only if root t belongs to f. That is, capital T is a square in f. And this is nothing but the simple application of the fundamental theorem. And another observation is that we can, if the discriminant is 0, then clearly one of them must be equal, and the polynomial is not separable, because some of the roots must be equal. Right? Okay. So let us begin by calculating the Galois groups of polynomials. Consider degree 2 polynomials. In degree 2 polynomials, we have the discriminant to be a square minus 4, and the polynomial is separable if and only if a square minus 4b is not equal 0. Otherwise, it will have equal roots. Also, we showed that a Galois group is always a subgroup of S2, as it is a degree 2 polynomial. And if the quadratic is irreducible, then the Galois group is S2, because if it is irreducible, the discriminant will not be a square. And if it is a square, then its Galois group will be 8, and A2 is nothing but the trivial group if D is a square in the base. So for example, you can take the example x minus 4x plus 2. You can calculate the discriminant. You can see that this is indeed a square in the base field, the discriminant, and also it can be factorized into like this. So D is a square in the base field, and the Galois group will be 8, and A2 is nothing but a trivial. Okay. Also consider the example x square minus 4. If you calculate the determinant, it will be a square, and so its Galois group will be trivial. Also, as discriminant of x square plus 2x plus 2 is minus 4, and minus 4 can't be a square over cube, we have the Galois group to be z mod 2. Right. So the calculation of polynomials of degree 2 is fairly simple, but we'll be reading that in degree 3 calculations as well. And I'll be showing you the calculation up to degree 3, up to degree 4. Okay. So assume that a cubic polynomial is fx equals x cube plus x square plus bx plus c. Now you make a manipulation. Substitute x equals y minus a by 3. So one thing might come into your mind that why this substitution is valid. Notice that if k is the splitting field of f, k is the splitting field of f, say f has roots alpha 1, alpha 2 and alpha 3, then if I do the manipulation alpha 1 minus a by 3, alpha 2 minus a by 3, alpha 3 minus a by 3, it won't matter, because a, this is already in the base, right? So the splitting field remains unchanged. Also, if I take the differences, alpha 1 minus alpha 2, this is similar to this is equal to alpha 1 minus alpha 3 minus alpha 2, right? So this gives the hint that the discriminant will also be invariant. Okay. So if we do this manipulation, we get P to be this and Q to be that. It's easy to check. Okay, so assume that the roots of the polynomial are alpha, beta and gamma. Then we can write g of y to be y minus alpha, y minus beta and y minus gamma. Product of these three vectors. Okay, and so this is nothing but the formal derivative. What do I mean by the formal derivative of polynomial? So if Px is a polynomial, this is a polynomial. Then I define the formal derivative. This is nothing but n times a of n x power n minus 1 plus n minus 1 times, to simply differentiate it, to n. So how is this formal derivative different from that we say in analysis? This is just a definition. It has no analytic terms. So we are not studying this derivative using limits, because in the base field f, the limits may or may not exist, because we might take the base field to be q also, or we might take it to be the real number also. Doesn't matter. So this is just a definition, a vague definition. So if we calculate the formal derivative, then we have y minus this term taken into every time using chain rule, and also one can check that these identities are true. It's simple to check. That is, the derivative is linear and also the derivative follows chain rule and product rule also. Okay. So then we have, if we place, if we plug in alpha, beta, gamma in place of y, we'll have these terms, and we'll see that the discriminant is nothing but a negative of the product of these two, right? And now the derivative is nothing but 3y squared plus 2, because the polynomial was y cube plus py plus p. So the derivative will be 3y squared plus p. So minus of p is nothing but the product of these three with alpha, beta and gamma plugged into it respectively. And as you can notice that this is a symmetric function in alpha, beta and gamma. So we can find out the symmetric functions from here, from this polynomial, S1, S2 and S3, and we can simply plug in, and we get the formula to be minus 4pq minus 27q squared. This is the formula of the determinant for the cubic case, and if we replace p and q by the original terms, then we get this formula. It's pretty huge formula. Okay, so to simplify it, we usually write it in this term, that is y cube plus py plus q. Okay. So if the cubic is reducible, then it either splits into three linear factors or a linear and a quadratic factor, where the quadratic factor would be irreducible. So if it splits into three linear factors, in that base field only, we can say that this base field itself is the splitting. So the Galois group will be trivial. And for the quadratic, if it splits into linear and a quadratic factor, we simply take the Galois group of the quadratic factor. Yeah. In the first case, the Galois group is trivial, as I said, and whereas in the second case, the Galois group is Z mod 2Z, as I showed in the previous case, the degree 2 case. And suppose the cubic is irreducible. So if the cubic is irreducible and I attach a root, that is alpha is a root of g1, then this is nothing but 3, as g is irreducible, we assume that. Then attaching a root to the base field generates an extension of degree 3. So what we can say that 3 divides the Galois. 3 divides the Galois. And also, from our initial assumption, not assumption, we proved this, the Galois group also divides S3, or also divides the order of S3, or is a subgroup of S3. So using this, we can conclude that the possible Galois groups can be S3 or A3. And when it is S3, we calculate the discriminant. standard procedure, we calculate the discriminant. We again check that whether it is a square or not. If it is a square, then the Galois group will be A3 as it fixes root over D, and if it is not a square, then it will be S3. Okay, so let us see some examples. For example, if we consider this polynomial, x cube minus x square minus 4 belongs to qx, it can be factored as x minus 2 times x square plus x plus 2. So you see that this can be broken into a linear factor and a quadratic factor, and the quadratic factor is irreducible. So what we do, we ignore the linear factor. As you see, the root 2 is already present in Q. So we are interested about the roots in x square plus x plus 2. And what we do, we attach a root of this irreducible factor to the original field, that is Q. And then we get the Galois group to go. The Galois group is nothing but 0. Okay. Another example. Okay, so we consider qx is x cube minus x plus 1 belongs to qx. Okay, so let me just review what rational root theorem was. So rational root theorem says that p over q is a root of nxn plus a minus 1 for n minus 1 plus a1x plus n1 if p divides a0 and q divides a. This is the rational root theorem. This is just a recall. So using rational root theorem, we can see that as it belongs to qx, the polynomial, we can say that the possible roots can be plus or minus 1, right? And if we plug in plus and minus 1, we can see that q of plus and minus 1 is both non-negative. So clearly, we can verify that it is irreducible as it has no roots. And another thing, if we are given a cubic polynomial, say fx is cubic, it would be reducible if it breaks into a linear and a quadratic term, or 3 linear terms. So it breaks into linear term, which suggests that there must be one root in the base field, which and this is true up to the degree 3 case only. And so we can conclude that a cubic polynomial is irreducible by studying its root, whether it is in the base field or not. So here it is not the case, so this is irreducible. And again, using the formula of the discriminant is minus 23, and clearly it is not a square in Q, the rationals, and so the Galois group will be S3. And another similar example, also using the rational root theorem, you can check that there is no root of Rx in Q, and so it is irreducible. Also, if we calculate the discriminant using the formula, it will be 49, and here it is a square in Q. So the Galois group is nothing but 8. Right. So now we come to degree 4 case. So degree 4 case is a bit interesting because in the cubic case and in the degree 2 case, what we saw is only a small number of groups which can be possibly the Galois groups of polynomials. That is S3, A3, Z mod 2Z and so on. But here we will see the emergence of some interesting groups. Okay, so consider the polynomial fx is this, then again standard procedure, we substitute x equals y minus a by 4, and I showed earlier that this does not affect the splitting field or the discriminant, so we get this polynomial. So this we do this basically to make the coefficient of x cube or x square vanish. Okay, so the p, q and r is given by this huge formula. Suppose alpha 1, alpha 2, alpha 3 and alpha 4 are the roots of G1. Okay. So we see cases. Case number 1 is the quartic is reducible. So if the quartic is reducible, then Gy splits into a linear and a cubic factor. This is a subcase 1. If it splits into a linear and a cubic factor, then the Galois group is nothing but the Galois group of the cubic factor, because the linear factor is already in the base. So that of the cubic. Also, if Gy splits into two if Gy splits into two irreducible terms, irreducible quadratic factors, then so suppose this is a these two are quadratic factors, then what we do, we take the discriminant of this, and we attach it to the base field f. Okay. So our splitting field is f of root d1, not root d, and root d. Another thing, we have two subcases here also. If d1 square is equal to some linear some constant times d2 square, then notice that attaching this, any one of this will work because alpha is in the base. And if not, if root d1 and root d2 are linearly independent, then the quadratic factors are, we just get a biquadratic extension like that we saw in Q to root 3. The Galois group will be a client for group which is isomorphic to Z plus Z mod to Z. And if not, this is nothing but f of root d1 if there is a linear relationship between them, and this is nothing but Z mod to Z. So we need to check whether the discriminants they form a linear dependence or not. Another case, the quadratic is irreducible. Another, we saw that the Galois groups must have transitive actions of the roots, specifically on the irreducible polynomials. So what we do, we only find out the transitive subgroups of S4. The possibilities are S4 and F4. These are two possibilities. Another one is the diagonal group of order 8. So diagonal group of order 8. Here it is nothing but it is generated by 1, 3, 2, 4 and 1. These two generate this 8. And the Klein 4 group, which is generated by possibility is the cyclic group of order 4. This is generated by 1, 2, 3. So these are the only options. Another thing, there are two more isomorphic copies of D8 in S2. For example, you can consider the three groups of D8. That is, one is 1, 2, 3, 4, 1 and 2. You keep this constant. Take 1 and 3, take 1 and 4. So these three are isomorphic copies. So we'll state only one, this D8. Okay. So these are the possible transitive groups, subgroups. Define theta 1 to be alpha 1 plus alpha 2, I mean this one. So these are again we call that alpha i's are the roots of the polynomial. And again you can notice that every element of D8 fixes theta 1. And the other two conjugate subgroups or the isomorphic subgroups, they fix theta 2 and theta 3 respectively. Also, the subgroup of S4 which stabilizes all the three is nothing but the intersection of all these D8s and their isomorphic copies, and we can verify it that it is nothing but V4. We calculate the symmetric functions on theta i's, and we can see by calculation that these are the symmetric functions. Then theta 1, theta 2 and theta 3 are nothing but the roots of the polynomial hx equals this one, and this is nothing but the cubic resolvent with the quadratic. Okay. So why do we need this cubic resolvent? So this cubic resolvent is needed for determining the Galois group. So if G dash is the Galois group of agents, that is a cubic resolvent, then one can check that G dash will always be a subgroup of G, because it already contains alpha 1, alpha 2, alpha 3 and alpha 4. In fact, the product of this, and so this is a subgroup of G. Okay. Now we calculate the differences of the roots. We can get that these are the expressions, And again, as you might guess, we will multiply this and derive the expression of the determinants. We can see that on multiplying and squaring, the discriminant of the quartic and the resultant cubic are the same. So the discriminant is this huge formula again. And we can calculate it using similarly the symmetric functions. Okay, so notice that the splitting field of the cubic resultant is a subfield of the splitting field. That is why the Galois group is a subgroup of this. So by the fundamental theorem of Galois group, this resultant is nothing but a quotient of G. So knowing the action of Galois groups on G dash might help in determining G. Right. So let us see some examples. Not examples, see the algorithm. So consider case 1. Case 1 is when the resultant is irreducible. So if the resultant is irreducible, then if D is a square, then if capital D is a square, then G is not contained in F. Then the only possibility is G is S. Right? And again we can see that if the cubic is irreducible, the resultant is irreducible, then the Galois group of the resultant is S3. Okay. And which implies that as order of S3 is 6, we can say that 6 divides 1G. And using these two hints, we can calculate that the Galois group is nothing but S4. Again, if D is a capital D is a square, the discriminant of the resultant is a square, then G should be a subgroup of A4. And also for the cubic, the Galois group will be nothing but A3. And order of A3 is 3. So 3 divides 1G by Lagrange, Lagrange's theorem. So the only possibility we get is G is A. So these are ones. Again, if the resultant is reducible, so if it splits into 3 linear terms, then what we can say? That theta 1, theta 2 and theta 3 belongs to F, which implies that G stabilizes theta 1, theta 2 and theta 3. Which implies that this will imply that G is a subgroup of B, and from this we can deduce that G is nothing but the Klein-Four group. Okay, so the interesting case is when it breaks into a linear and a quadratic factor. So, if it breaks into a linear and a quadratic factor, the possibilities quadratic factors, then G stabilizes any one of theta 1, theta 2 or theta 3. As it will be of the resultant will be of the form x minus theta 1 x minus. This is a quadratic, irreducible quadratic factor. Irreducible quadratic factor. So G must stabilize theta. So the possibilities are either G is D8 or C4. These two are the possibilities. And by the fundamental theorem, if we attach root D to F, we get that F of root D with the speed speed of this one. This is the Galois group. So we need to calculate two groups. One is the possible groups are D8 and C4. So one is D8 intersection A4 and another one is C4 intersection A4. And this is nothing but the Klein-Four group. But C intersection A4 gives us this. And this we saw that this is not a transitive. So we will discard this. Now, we will see that if Gy is irreducible over F root D, then only this case falls. As this B is transitive on the roots of Gy. So Gy has to be reducible. Also, another interesting result which I am not proving, I am just stating, if that over Q, the Galois group cannot be cyclic if the discriminant is not the sum of two squares. Then only the Galois group has to be cyclic of order 4. Okay, so now we'll move on to another topic, Vandermonde matrix and Newton's identity. We'll see some examples of the degree 4 polynomial at the end of the talk. Okay, so we define if A1, A2 up to A3 belongs to K for some field, then we define the Vandermonde matrix like this. Up to n minus 1th power, the entries, and we can prove by induction that the discriminant, the determinant of the Vandermonde matrix is nothing but this, and this is nothing but the root of the discriminant, square root of the discriminant. This can be proven easily by induction. Okay, so now we'll use the determinant of the Vandermonde matrices to calculate the discriminant. Okay, so another observation: if I take V transpose V, then I get this matrix. This matrix P1, P0, P1, this will be P2, P2, Pn minus 1. Like this, where Pi's are nothing but there's a summation of H over R. J is from 1 to n. Right. These are just the sum of the powers. And this is nothing but determinant of V square. Standard linear algebraic. Determinant of this will be determinant of V square. Okay. So this will help us to calculate the discriminant of the polynomial. Another thing, we'll state the Newton's identity. So let SI be the elementary symmetric functions on alpha is. And for I greater than n, assume that SI is a 0. And so if Pi are the sum of the powers, then we get this identity. This alternating sum equals 0. And this will help us calculate the discriminants. For example, if you consider the old polynomials, x cube plus px plus q, then by Newton's identity, I mean, if I clearly state the identity, then it will be the form. We'll be using this. P1 minus S1 is 0. P2 minus S1 P1 plus 2S2 is 0. P3 minus S1 P2 plus S2 P1 minus 3S3 is 0. And so on. And another for P4. Okay, so P4, mind one thing that in P4 we'll be using the term S4, and S4, as I defined that for I greater than n, S4 will be 0. So using this we can get the P1, P2, P3 and P4, and we plug it into the Vandermonde matrix identity. So discriminant is nothing but, so we'll be using this one. This is nothing but discriminant squared, as I showed that the determinant is nothing but bundle of discriminant. So the discriminant is nothing but the determinant of this matrix. And again, you can check that this is nothing but minus 4pq minus 27q square, the formula that we obtained earlier. So this is an interesting application. And another interesting application is the resultant of two polynomials. For me, this is the best application for calculating calculating the discriminant of a polynomial. So, resultant of two polynomials. So let fx and gx be two polynomials defined like this, and factorize the polynomials as fx like this and gx like this. Alpha i's are the roots of f and beta i's are the roots of g, and the leading term is n and pm respectively. So if we denote by pk the space of polynomials of degree k minus 1, so this is a vector space of dimension k plus 1. We define a function. The function is, you can check that there is a linear transformation also, rho, from the space of polynomials of degree less than equals n minus 1 or n to n plus n minus 1, where u comma v maps to f of v plus g of v. F and g are defined as above. Okay, so one thing you can notice that this is a linear transformation, you can easily check. So we'll derive a matrix representation for this, but before that let me state one lemma. The lemma is if kernel of rho is not equal 0, then the polynomial, if the kernel of rho is 0, that is not equal, it is equal 0, then the polynomials f and g have a common root. And the proof is fairly easy. So let u v belong to kernel of rho. Assume that f and g have no common root. Okay, so u and v belongs to kernel of rho. It implies that f equals minus g. Also, fx is a unique factorization domain. So we can state that v has roots alpha 1, alpha 2 up to alpha n, because this holds, and u has roots beta 1, beta 2 up to beta n. But u and v have degree less than equals m minus 1 and less than equals n minus 1. And the roots are n, and clearly when we have the number of roots to be more than the degree, we have u and v to be identically 0. So if they have no common roots, the kernel is trivial. So we show the contrapositive part. And the other part, conversely, if f and g have a common root, let us take the common root to be gamma and define v to be fx by x minus gamma and u to be minus gx by x minus gamma. Then you can clearly show that f u plus g is 0. So u comma v belongs to kernel. Okay, so this is the lemma that we use. Okay, so for the polynomial space, the basis will be x bar k minus 1, x bar k minus 2 up to 1. The matrix representation is nothing but we multiply. So we just take the coefficients. Let me not show that. We take the coefficient and just place it like this, and then we again multiply it by x, so the degree increases, and then we place the coefficients like this, and so on and so forth. We continue up till this. So this part is of these are m rows and these are n rows. Okay. So the first is m rows and the second is n rows. So we get the matrix representation like this. So this is called a Sylvester matrix, and the order of the matrix is m plus n plus n plus n. And the resultant of f and g is nothing but the determinant of row, that is this matrix. Okay, so now we will derive a term, a closed formula for RFG. So proposition RFG can be written as an power n, bm power n times product of these product ranging over I1 to n and j1 to n alpha I minus beta j. Okay. So some observations. We can see that our previous lemma holds true, that if they have a common root, say some alpha I is equal to some beta j, then clearly the resultant is 0. So we can say that f and g have a common root. This is an if and only condition. And also, we can verify that from this formula, if we assume it is true, then R of fg is nothing but a power n g of alpha, or we can use this also, minus 1 power mn b of n power n, b of n power n, product of equals 1 to n, sorry, f of beta j. You can use this formula, but I will be using this one. Okay, so let us see the proof of this proposition. So by our lemma, we saw that this holds true, the determinant is 0 if and only if alpha equals beta j for some ij. So one thing we can say for sure is that the resultant is divisible by this double product. Okay, so because we see by the lemma. Another thing. Okay, so this is nothing but the Vieta's relation. The Vieta's relation on the polynomial states that the coefficients can be expressed in this. A minus 1 is nothing but minus n times alpha 1 plus alpha 2 plus alpha n, and a0 is nothing but this. In other words, this is nothing but an can be an minus 1, or the ai's can be expressed as the leading coefficient times the symmetric functions on alphas. And as you can see that all the coefficients from a0 to n minus 1, they have one an in common, and so we'll be exploiting this property. Okay, so another thing, if you notice that we had the determinant of the Sylvester matrix that we saw previously, this one. From each of these terms, we can take, from each of these rows, we can take one an common, and we have m such rows. And similarly, from this bm, we can take that bm common from each row, and we have n such rows. So we can reduce that an power m times bm power n, and this product, this divides the resultant of f and g. Okay. So our goal is to show that these two are equal. Okay, so another trick, this is nothing but, this is a tricky proof, this is a very good proof actually. So if we expand the determinant of the degree of AIs and if we expand the determinant, we see that the degree of AIs is m and that of Bj's is n, which I already stated below above. So if we use this formula, this is nothing but this expanded. So what we can see is, okay, so the degree of Bi's is indeed n because the product is taken up to n, I equals 1 to n. So the degree of Bj's is indeed n. So from the determinant we can see that the degrees match, and from the RHS we can see that the degrees match. So by comparing the degrees on both the sides, we see that the LHS must be a constant times of the RHS. Now we will prove that this constant is nothing but 1. So for that we expand the determinant, and if we expand the determinant, we will see that the coefficient of an power n times b0 power n is 1. Again, this is the LHS, that is the coefficient of an power m times b0 power n is 1 in the LHS, and in the RHS, if we expand, we will see that the b0 term is taken n times product, and we have an here. So again, this will be the coefficient of n power m and b0 power n is nothing but 1. So from this we can deduce that this will be equal. We prove that the constant is nothing but 1. Okay, so this was the proposition that we wanted. So the next proposition will bridge the gap between the resultant and the discriminant, and we'll use the resultant of the polynomial to calculate the discriminants. So let us see the next here. So the resultant of f and the formal derivative of f is nothing but this times the discriminant of f. And if we see the proof, we have fx is nothing but ax times an times this one, and if we take the derivative, we will apply the chain rule, the product rule, and obtain this, and we plug in one alpha k, and then this sum will vanish and we'll have this term only. Okay. Simple enough till now. Okay, so out of f and g we have an power n minus 1 times k minus 1 product from k to 1, from k1 to n f prime of alpha k. And clearly you can see that we plug in the value of alpha k here, and we get this an power 2n minus 1 times this. And I'm skipping the calculation, but you can see that if we manipulate the exponent of minus 1 and we use the fact that discriminant is nothing but this. Okay, so here you can see a term of an coming extra. So I discussed the discriminant for monic polynomial, and this is a general one whose coefficient of leading term can change. So this is nothing but an times 2n minus 2 times the product of this. So if we manipulate this and using the fact we have this, we will get the resultant of f and f dash is nothing but this times the discriminant of f. So remember that for the resultant part we had the Sylvester matrix. So now we will just compute the determinant of the matrix and just make this adjustment, divide by this to get the discriminant. So this is the best method according to me. So consider the polynomials of the form xn. So this is an example. Xn plus px plus q. Then the corresponding Sylvester matrix is of the form this. So again you take the coefficient of 1, place it here, and then the coefficient of p and q, and the rest of them are 0, and continue like this. And again if you take the derivative, it will be nothing but nx power n minus 1 plus p, and so it will be nothing but this. So if you compute this determinant, again I am skipping the proof, the calculation. So you will get that, and using the relation between the discriminant and the resultant, we get this nice formula. Not nice, it's pretty huge, but still nice. The computation method is nice. The discriminant of this xn plus px plus q. Okay, so we got a general method for finding this discriminant. Otherwise, if this method is not used, then it will be of great difficulty to consider general polynomials like that of degree n. Okay. So I told you that I'll show some examples of degree 4. So now let us consider this. consider fx is x bar 4 plus 4, and by Sophie-Germain identity we can factorize it like this. But we can see that the discriminant of both of these factors, b square minus 4ac, the discriminant formula of the quadratics, these are both the same. So it does not matter if we attach both of them or just one. The Galois group will be z0 2z. If the discriminant of this would have been such that root of d1 is not equal to some value for all alpha, then the Galois group would have been z0 2z, direct product z0 2z. Right. So this is one example. Again, consider fx is x power 4 plus 2x squared plus x plus q, x plus 3. Then using the formula for the resolvent polynomial, we see that gx is nothing but this. Again, using the rational root theorem, we see that there are no roots of gx in q. So gx is irreducible because I explained it earlier, gx is a cubic polynomial. So gx is irreducible, and again if we use the formula of the discriminant, we see that 3877, which is the discriminant, is not a square. Again, the Galois group is nothing but s. So consider this example. This is a pretty interesting example. So before moving on to this example, I will discuss two things. So remember that for a irreducible polynomial or irreducible cubic polynomial, we saw that if f is irreducible cubic, if f is irreducible cubic, then possible Galois groups can be S3 or A3. Now, when we had A3, when D was a square in F, and we had S3 if D was not a square in F. So, by fundamental theorem, we see that order of A3 is nothing but 3 and order of S3 is nothing but 6. So, by fundamental theorem, we see that the field extension must be of degree 3. And here it must be of degree 6. So we can interpret it in terms of the determinant, discriminant, and a root. So if the Galois group is A3, it means that it implies that D squared is a square. D is a square in F, and as D is a square in F, this is nothing but, by the fundamental theorem, we take a root of the irreducible cubic, that is theta, and attach it to the base value. So this is because of A3. In general, what we do, if D was not a square, that is root D, if it did not belong to F, what we do is, we would attach a root which is of degree 3, and we would attach the square root of the discriminant. Right. So this is a field, the extension of this is of degree 6, and for this is of degree 3. Again, if you want to explicitly state the automorphisms that we get for the elements of the Galois group, we can show that if the generators of the Galois group is a sigma and tau, and what is sigma? Sigma takes theta to some other roots and fixes root D. Right? This will be an element of order 3 in the Galois group. And tau fixes theta and maps root D to plus minus root D, and this will be a generator of degree 2. Okay. So this is a way of interpreting what we actually do to the splitting field of the cube. We attach, again to recall, we attach one root. We attach a root and the discriminant in general. And if the discriminant is a square, well and good, this is a extension of degree 3. And if it is not a square, then it will be an extension of degree 6. Okay. And another fact that I'll be using in this example is, so if we take two composite fields, that is if K1 and K2, these both are field extensions of F, then Galois group of K1, K2 over F is isomorphic. Okay, so we have another additional condition, that is K1 intersection K2 must be the base field. So then Galois of this is nothing but K1 Galois group of K1 over F, direct product with Galois group of K2 over F. So this will be using in this example. So consider the polynomial x power 5 plus x minus 1, and it can be factorized as x square minus x plus 1 times x cube plus x square minus 1. So the discriminant of f1, if we denote it by f1 and f2, the discriminant of f1 is minus 3. So we attach the discriminant minus 3 with q, and we get the field to be k1 is q of minus 2. Again, if we take k2, then as I discussed it here, we attach a root, and we attach the discriminant. As the discriminant is not a square, we can calculate this to be minus 23. We attach this to get the splitting field, that is the Galois group. And a simple exercise is to check that K1 intersection K2 is nothing but Q. So this is a simple exercise. So we can conclude that using this lemma or this theorem, that Galois group of K1 K2 over Q is nothing but Z mod 2Z because x square minus x plus 1 is irreducible, and S3 because this is irreducible and the discriminant is minus 23. So we can express it as a direct product of these two. So this was a good example. Again, consider the polynomial x power 4 plus 4x minus 1. So this is the case where the resolvent will be factorized into a linear and a quadratic. So if the discriminant is minus 7168, and that is nothing but minus 32 square times 7, and clearly it is not a square. The resolvent cubic is nothing but this, which can be factorized as this. So as the resolvent can be broken into a linear and a quadratic term, we come into a last case, that is it can be D8 or C4. So one is clearly using the formula, using the theorem that I stated, that if the discriminant cannot be expressed as a sum of two squares, then it can't be C4, which is clearly the case because this is minus 7168 and can't be expressed as a sum of two squares. But if we want to do it in the lengthy way, that is if we want to show that it is D8, we needed to show that fx is irreducible in q of root d. Root d is the discriminant, and again here I have taken minus 7 because already 32 is a square, so we need not consider that because 32 is already in the base field. So we have taken it to be q of root of minus 7. So this is a bit lengthy procedure. Again, you can solve it simply by concluding that the discriminant can be expressed as sum of two squares. So if we denote by t, one of the square roots of minus 7, let sigma be the automorphism sending t to minus 2. Then automorphism of q of root of minus 7 over q is nothing but 1 over sigma, because this is irreducible. Okay. Now as f is irreducible over q, we attaching a root of f generates an extension of degree 4 because f was a degree 4 polynomial. So clearly, if the resolvent is of degree 2 and this is of degree 4, if we attach a root, then clearly fx has no roots in q of minus 7, root of minus 7. So one thing is for sure, that if it is reducible, then it must be in the form q1x, q2x, where these two are quadratic factors. Okay. And it will not be in the form of some linear times some cubic, because if we attach a root, then it generates an extension of degree 4, and the base field and this is an extension of degree 2. Okay. So now the only possible factors are the quadratic factors. Let qx be an irreducible factor, and if you use the isomorphism extension theorem, then you can get that as f is defined over q, then sigma of q of x is another quadratic factor of fx. So fx must be q of x times q of minus x. Again, let me remind what was sigma. Sigma was nothing but the automorphism sending t to minus t, where t is one of the square roots of minus 7. So we get this decomposition. Fx is qx times sigma of qx, which implies that f of 0 is q of 0 times sigma of q of 0. Now, if we assume that q of 0 is some a plus bt, because q of 0 is an element of q of root of minus 7 and t is a q of square root of minus 7, then sigma of q of 0, as sigma fixes a and b, is nothing but a minus bt. So f of 0 is q of 0 times this, and this is nothing but a square minus b square t square, and t square was nothing but minus 7. So we get that a square plus 7t square, and this is f of 0. And mind that we had f of 0 to be minus 1. So what we get? We get a square plus 7t square is minus 1, where a and b belongs to the base field q, that is the rationals. So as this is negative, this clearly is not possible, as this LHS is non-negative. So we get a contradiction. So clearly we can conclude that fx is irreducible over q of root 7, q of root of minus 7. So the Galois group must be D. Again, this is a bit lengthy procedure. You can use that sum of two squares proposition to conclude that this is the Galois group is D. Okay, so one last example before we end the talk. Consider a polynomial of polynomial fx x bar 5 minus 6x plus 3. So this is, if you check that this is Eisenstein at 3, so let me recall Eisenstein's criteria. So if qx is this polynomial, and this belongs to c of x, that is the coefficients are integers, if there exists prime p such that p divides ai for I less than equals n minus 1 and greater than equals 0, 2, p does not divide an, and the third condition is p square does not divide a0. If these three conditions are satisfied for some prime, then this qx is irreducible. It's a pretty good theorem or condition to check for irreducibility. So this is irreducible in q of x, that is the rational field, the ring over rational field, and again by Gauss's lemma we can conclude that if it is irreducible in q of x, then it will be irreducible in 0 of x. Okay, so this was just a recall of the famous Eisenstein's criteria, and if we consider the polynomial fx is x power 5 minus 6x plus 3 belongs to qx, check that this is Eisenstein at 3, that is 3 satisfies this condition, so it is irreducible. So as it is irreducible, if we attach a root, this generates a degree of extension 5. So one thing for sure, 5 divides the degree of the splitting field. Another thing we learn in group theory is that if P is a prime, if G is a finite group, and P be a prime dividing the order of G, then there exists then there exists an element of order P in G. This is for P prime. Right? So we saw that 5 divides the degree of the extension of the splitting wheel, that is, divides the order of the Galois group. So one thing is for sure that 5 is a prime, and so G has an element of order 5. Okay. Another thing we can check that we just apply simple real analysis. We apply intermediate value theorem. We check the value of f at these 4 points, and we can see that the sign is changing. So one thing is for sure that by intermediate value theorem, fx has a root in these 3 intervals: -2, 0, 0, 1, and 1, 2. If you study the derivative will be the derivative is increasing in both the intervals 2, infinity and -infinity to -2. So then we can conclude by this, and by seeing the graph of this polynomial, that there are 3 real roots and 2 complex roots. Okay, so we have 2 complex roots, but notice that the coefficients are in the rational field. So one thing we can deduce that the complex roots must be the conjugate of each other. So as there are 2 complex roots and they are conjugate of each other, there must exist an automorphism corresponding to complex conjugation. That is, there exists a sigma sending a plus bi to a minus b. Okay, and clearly this automorphism is of order 2. Now we have an automorphism of order 2 and another automorphism of order 5. And from simple group theory knowledge, we can state that a cycle of a 5 cycle and a 2 cycle together generates S5. So we can conclude that a 5 cycle and together with the transpositions or 2 cycles generates S5, and so S5 is our Galois. Okay, so this was the end of the talk, and before ending, let me give some conclusion and another interesting fact. Galois group provides a powerful perspective from which to study polynomial equations. If we know the Galois group of a polynomial, then the behavior of its roots can be understood by accessing many of the truths of group theory. Like we saw the previous example, we studied cycles and some other methods. We studied irreducibility over some specific fields to deduce the Galois groups. So the insights we gain through this approach are far more illuminating than the ones we can get by performing algebra on the polynomial itself. For instance, the Galois group immediately tells us whether a polynomial is solvable or not. Again, I have skipped the solvability part in this talk. So if I want to state something in general, in the beginning of the talk I stated that polynomials of degree 5 and onwards, they are irreducible. That is, we can find an explicit formula for the roots of these polynomials. This is because the group Sn is insoluble or is not solvable for n greater than equals 5. Galois groups can also be used to study various mathematical objects in algebra and number theory in ways that open up solutions to problems that aren't otherwise available. For example, but I don't know the details about it, but I have heard that Galois groups, the computation of Galois groups, these are used in the Langland's program, which is studying algebraic number theory. Okay, so another interesting fact to conclude. So I think you all know the infamous death of Galois while dueling. So Galois died on March 30th, 1832 in Paris dueling ground. So legend has it that the night before he stayed up late finishing his manuscript, his last manuscript. Then he wrote, "Go to the roots of these calculations, group the operations, classify them according to their complexities, rather than their appearances. This, I believe, is the mission of future mathematicians. This is the road on which I am embarking this work. Who knows what mathematics might have witnessed if Galois had survived the duel method." Thank you. And here are the references that I used. Abstract Algebra by Dominican Foot, Field and Galois Theory by Patrick Morandi. And this paper is particularly very interesting. This contains many properties and theorems and propositions about resultants and discriminants and many more such algorithms or computation methods of resultants, and this is by Semantic Johnson. Okay, so that was all. Thank you.
Any questions? If not, we thank our speaker once again.